Okay, so what I want to talk about in the next really three videos is rate of changes and how they are useful and important in finance as it is particularly relevant to being an actuary. Okay? And the general title of this topic is, as you can see, the force of interest. So if you want to look that up in Google, force of interest, um, yeah, we're going to talk basically about that. All right. And I'll explain what that precisely means in a moment. Okay, so you've all have seen rate of changes. It might have been a while. So let's say, as usual, A of t is the amount in an account after t years. Really, A of t could be anything for the purposes of rate of changes. All right. So the average rate of change from some time t0 to a future time t1, whatever they are, is given by the usual formula, just the difference quotient. All right. And practically, what does this mean? It means that the amount you have at the end of your at your second time at T1 is given by the amount you have at T0 plus the average rate of change times the change in time. In other words, the amount that you've grown by is precisely the average rate of change times the change in time. And you can kind of think of this as like an average speed over this time interval. It might be more practical to just kind of think of it like this. Again, the amount that you've grown by is precisely the average rate of change times change in time. So, for example, let's say after 1 year, you have an account with $930, whereas after 9 months, um, the account had $900. Okay, so clearly, you've grown by $30 in this 3 month time period. So we'll check that according to the formula that I mentioned a second ago. But yeah, you just plug this into a calculator. Your average rate of change is $120 per year. And the formula I had here checks out. And I'll just plop this into the calculator to double check this. Bear with me a second. Right, so we have 900, how much the account had after 9 months, plus the average rate of change, 120, times change in time, 1 minus 0.075 in years. Sorry, it was 0.75. Sorry about that. So 900 plus 120 times parentheses 1 minus 0.75, and we get 930. And yeah, if you just take the average rate of change times the change in time, we get $30, which is, of course, how much you've grown by exactly in this 3 month period. Okay. Now, this is all great and everything, but it's not particularly useful in finance because in business, economics, et cetera, for the simple reason that, um, well, what's important is your rate of change relative to how much you're making, how much is in the account. So, for example, if your account is how much you're making, uh, if you're a multi-million dollar company, you really don't want to be growing by $120 a year. That's pretty slow. It'd be much better to grow by much more. On the other hand, if you have a part-time hobby of making jewelry, you know, and you just do it for fun mainly, you might be very happy making $120 per year, growing by $120 per year. So yeah, what's important is kind of what your rate of change is relative to how much you started off with in the account. Okay, and the formula for that is the same thing. You just divide by how much you have in the account at the beginning. Right. And this has very important and practical meaning. And the practical meaning of this formula, what it gives you, is this valuable information of the percentage growth, as we've done many times in prior videos, over this time interval, is this relative rate of change times change in time, just turn to a percentage times 100%. All right, so for example, you plop this into the calculator, you're going to get 0.1333. Threes go on, but you're going to basically get 0.13333 rounding per year. And again, what does that practically mean? That means if you take this times my change in time, convert it into a percentage, you're going to be growing by 3.333% over this 3 month period from 9 months to 1 year. Okay. And let's just check that. Let's just quickly check that. 1 second. I usually have the financial calculator, but I do not have the needed dongle for it. So, um, right. So here, all right. So let's take, yeah, we start off with $900. Sorry about that. And let's say we're growing by 3.333%. That means we're going to multiply by 1.033 3. Let's see how many threes I had. I had 3 decimals, so I'll add another 3. Sorry about that. So what does this give me? It basically gives me $930 as we need. Right? So if we start off with $900 and we grow by 3.333% in this 3 month period, we're going to get $930. So this checks out. Okay. Okay. Well, what we're interested in, and as an actuary, you rarely, well, not rarely, you generally don't look at short-term, uh, kind of financial things like stocks, commodities, et cetera. But as sort of just like a little baby introduction to modeling kind of short-term financial products, what we're interested in is a relative rate of change for very small time. Just like in physics, just like in economics, it's much easier to look at the instantaneous rate of change, relative rate of change, rather than the relative rate of change for a tiny time interval. So, more precisely, let's say we're looking at my time interval from some time t. We're starting off at some time t, and then adding some little h to that time. And as we usually do in calculus, we're going to let h go to 0. So this is my t0 here. This is my t1 here. So, yeah, this is the relative rate of change starting at t and ending at t plus h. And we're going to let h go to 0. And this gives us this very convenient formula, because this is just a derivative, a prime over a. And this is what's called the force of interest. And we'll see in later videos examples of approximating a relative rate of change over a small time interval by this quantity here. And it turns out for small time intervals, let's say a day or two, or even 3 days relative to a year, so you might want to see how an account changes over 3 days, 2 days. This really gives a amazingly accurate approximation to the relative rate of change over this relatively small time period. Again, maybe a day or two compared to a year. All right, and yeah, this quantity here is what's called the force of interest. So what we'll do next is some very easy examples on computing this. What is much more interesting is, and this is what's mainly tested on Exam FM, if you're given this force of interest, I'm not sure why they use delta T, but this is standard actuarial notation. So if you're given this force of interest, how do you recover the A function, the accumulation function? How much is in the account after T years? That's actually quite interesting. It's a really beautiful application of the chain rule and the fundamental theorem of calculus, but we'll do that in the next video.
Okay, so right, so let's do some easy examples. Right, let's find delta of t in the situation where we have compound interest and we make one single deposit into this account at t equals time 0, and then we see, based on that one single deposit, what happens. All right, so let's just write down the function that we're finding the force of interest for. It's A0, A0, same thing, 1 plus I raised to the power t. Okay, so we when we find the derivative, of course, we can pull out the A0. So we're finding the derivative now of 1 plus I raised to the power t. And just a reminder of how to do that. Well, remember that whenever I have a positive constant t and I raise it, positive constant a, and I raise it to the t, I take the derivative that gives me a raised to the t times ln of a. So it's its own derivative, a to the t, except for this ln of a here. All right, so of course here a is 1 plus I. So this is going to be a naught times, well, it's I'll stick the ln of a in front, the ln of 1 plus I. Actually, I'll stick it, just do it exactly as I have here. So it's 1 plus I to the t times ln of 1 plus I. Again, this is my a, so I'm just doing exactly what is here, what is in this box here. All right, so now just plug and chug. It's a prime by definition, a prime over a. So it's a0, 1 plus I raised to the power t, ln of 1 plus I over, well, a of t is a0, 1 plus I raised to the t. So this whole thing right here cancels out. So you get that we have a we have a constant force of interest. So what this says is compound interest corresponds to a constant force of interest. And we'll actually in the next video go backwards. We will show that if you are given a constant force of interest, you can recover the compound interest formula, a of t equals a naught 1 plus I to the t, just from that, that constant force of interest. Okay. Yeah, so let's do another very simple
example, and that is, let's find the force of interest when we have simple interest. And the answer is going to be not as simple as it is for compound interest. Right, so let's do that. Okay, so A of t here is going to be, well, A naught 1 plus I times t. Right, so let's get the derivative here. So this is just going to be A0 plus A0 I times t. So when you differentiate, the constant goes away. So just differentiate both terms. I can pull out the A0 I and just differentiate t here. So then this is just A0 times I times 1. Derivative of t with respect to t is just 1. Nothing really there too much, so just plug and chug. Sorry, that should be a t here. And this is going to be A0I over A0 1 plus I t. That's what A of t is. So not nearly as much stuff as before cancels out. All we can really do is cancel out the A0s. You definitely do not want to say the I's cancel out. It's just not correct algebra. So we get that this is going to be 1 plus I over 1 plus I to the t. So this corresponds to a force of interest. Delta t is going to be equal to, maybe just make this a little smaller. So my force of interest here, sorry about that. This is going to correspond, this is going to be I over 1 plus IT. So yeah, we do not get a constant force of interest when we're dealing with simple interest.
Well, what's more important and more useful is if we're given the force of interest, how do you reconstruct the amount in the account? Okay, so how do you recover A of t from the force of interest? Now, this is a very, very generic kind of concept for doing that. Whenever you have instantaneous rate of change in any context, finance, biology, engineering, whatever, the logic I'm going to employ here allows you to recover the original quantity. Right? And the key observation here, and because this is so generic, I think it's very worthwhile to understand where this is coming from. So the key observation is if we take the derivative of ln of A of t, we use the chain rule. It's a derivative of the outside with the inside plugged in. Derivative of ln is 1 over. Plug in A of t into 1 over. It's 1 over A of t. That's the A of t in the bottom. Times the derivative of A, the derivative of the inside. The inside, again, like I said, sorry, is A. So it's times A prime of t. So it's really 1 over t times A prime of t, which is A prime over A. And that is the force of interest. That is our instantaneous relative rate of change at time t. Okay. Now, how on earth does this help us? Well, if you're astute and if you've seen this before, well, you know what's coming. If you haven't, but you're astute, then you might be able to think, and you should be thinking, hey, wait a minute, I can get rid of this derivative I want a of t, and I can get rid of this derivative by integrating. And then maybe I can solve for a of t once I get rid of this integral. Sorry, once I get rid of this derivative. Okay. So we integrate both sides from t0 to t1. All right. This is just what we got. Delta of t is the derivative of ln of a of t. Okay. Now I do the fundamental theorem. The integral undoes the derivative, and I'm just going to plug in t1 and then plug in t0. But here's my integrand. It's ln of a of t. So it's ln of a of t1 minus ln of a of t0. All right, so what I'm going to do is now exponentiate both sides. I'll just quickly go through this. Let's see if I can. 1 second. Make this a little. There we go. Should be enough room. Okay, so what do I have here? Sorry, one. There we go. Make this a little bigger. Okay, so right. So let's just take this whole thing here and exponentiate both sides. So I have I have e to this integral here. And this does look a little funky, I have to admit, but it is what it is. You know, there's no way around the funkiness. So t0 to t1, delta of t dt. That's going to be e to the ln a of t1 inside the e ln a of t0. Okay. So we know, or we should know, that whenever we have e of something minus something, it's e to the first something over e to the second something. So it's going to be e to the ln a of t1. And I'm just doing this also so that it doesn't look like some weird magic on how I solve for a of t1, which is what we really want in terms of a of t0. So it's ln a of t0, right? Move this up a bit. Okay, well, e undoes the ln. So we have a of t1. Again, e undoes the ln over a of t0. Okay. All right, so yeah, we can take this here. And, well, if we just multiply by a of t0, what I'm putting in a circle, we get exactly what we want. A of t1 is a of t0 times e to this integral. Okay. Now, there's a little bit of a caveat here. For a lot of these problems that we're going to see, for the exam FM problems, it's sometimes a little murky exactly when this formula is true. A good rule of thumb is you use this formula only if one single deposit is made at some time t0. So if you have a problem with multiple deposits or withdrawals, you just break the problem up into, you break it up into the problems involving one single deposit. And I'll do an example. What do I mean by that? Okay, so let's say we have an initial deposit of 500. And a deposit at the end of the third year of 1,000 is made. Let's find out how much is in the account after 6 years if the force of interest is given by t over 10. Okay. So what we're going to do is we're going to break this up into two kind of problems. We're going to kind of consider we're going to consider the 500 by itself, see what happens after from this initial deposit at t equals 0 to t equals 6. Okay. And then we're going to look at by itself our 1,000 deposit at the end of the third year, which is right when t equals 3, and then see what happens from the end of the third year to the end of the sixth year from that 1,000 deposit. We're going to do that separately so that we're not violating this general rule of thumb here. All right.
Okay, so let's break this up into two pieces here. And I'll do it, I'll also do this problem a different way that maybe is a little more efficient, but maybe less conceptually, or maybe it's a little more conceptually complicated. But either way, I think is fine to do it on quiz or exam homework. All right, so let's say A of t is the amount after t years from the $500 deposit or from the 500 initial deposit at t equals 0. So here t is bigger or equal to 0. We just want to see, in particular, after 6 years, how much the 500 grew. And we can let's do B of t corresponding to the $1,000 deposit separately. So remember, to apply our formula, we really can only have one single deposit, or we can only really have one single deposit or withdrawal being a negative deposit, essentially. But we can only have one single deposit in order to use our formula, so we just consider the deposit separately and separately apply our formula. So let's say B of t is the amount after t years from the $1,000 deposit after 3 years, which is at t equals 0. And so this means t is bigger or equal to 3. Right? So we're looking at B of t between t equals 3 and t equals 6. In particular, we want B of 6. So the final answer is just going to be B of 6 plus, A of 6 rather, plus B of 6. We figure out how much the $500 grows after 6 years, and we figure out how much the $1,000 grows after 3 years. Okay. Okay, so, right, so for A of 6, well, we're going to use our formula, and I'll remind you of the formula in a second, but we definitely need we need this integral here, 0 to 6, okay? And just to make clear, this right here is my only deposit whatsoever, just considering the $500 deposit and seeing how it grows. When I write this A of t, I'm not considering any other deposits. I'm only looking at one single deposit, so I can just plug and chug into my formula to get A of 6. Okay, so here, this is going to be my T0, my deposit of $500 is at T0, and I want A of 6, so that's my T1. Okay, so, right, so plug into my formula, of course, I need to get this integral first. And if this formula is just really funky looking, I do recommend just doing this integral first. So my delta, my force of interest rather, is t over 10. And so this is going to be, just integrate t squared over 20 from 0 to 6. And so that's 36, well, minus 0 over 20, or 6 squared minus 0 squared over 20. So it's 36 over 20. So my formula, just plug and chug, a of 6 is a 0 e to the integral t0, t1, delta t, dt. And again, a 0, well, my initial deposit is 500, so let's plug that in. T0 is 0. It's when the deposit occurs. And T1 is 6. Okay. And, well, this is t over 10, but so I'm just plugging in for this integral here. So we got it as 36 over 20. So it's 500 e to 36 over 20. And this is going to be, because I don't have to really do anything further with this amount, I'll just round to the nearest cent. 3,024.82 cents. All right, so let's get b of 6. And you gotta be a little careful, not super careful, but we gotta be a little careful because here, well, my deposit occurs not at t equals 0, but it occurs at t equals 3. So here, this is my t0, this is my t1. I want b of 6, and the deposit occurs at t equals 0. And that's very important because, you know, this delta of t, remember, is kind of like a continuously varying interest rate. So this reflects the fact that this interest rate here is going to look a lot different at t equals 3 after 3 years than it might look at the beginning, t equals 0. You know, this could have been that t equals 0 is, let's say, pre-pandemic, and t equals 3 is, I don't know, halfway into the pandemic. I mean, maybe that's not a great example because even pre-pandemic interest rates were still pretty low, but they weren't as low before the pandemic as they were now. So maybe it is not that bad of a example. But anyway, this might look very different after 3 years than it does at the beginning. So anyway, so this is a nice, again, nice easy integral. So this is going to be t over 10 dt. So t squared over 20, 3 to 6. So it's going to be 6 squared minus 3 squared over 20. Yeah, and I apologize if I'm insulting anyone's intelligence by actually doing these integrals slowly. I hope I'm not, but and it's not wasting too much time, even if I am. But anyway, so it's 27 over 20. So, right, I guess I'll just write it exactly like I did here. B of T1, or I had it and erased it. It's going to be that. B of t0 e to the t0 t1. Move this 20 up a bit so it doesn't look like it's part of this here. Delta t dt. And again, t1 here, we want b of 6. We want to see what happens to the $500 after 3 years, which t equals 3 to t equals 6 is, well, that's 3 years. So t1 is 6. We want it at t equals 6. Our initial time is 3. And of course, b of 3 we're given is 500. So plop in 500 here. This is 3, this is 6. And we got this to be 27 over 20. So 500, sorry. The initial deposit was 500. The second deposit is 1,000. Apologize for that. So it's 1,000 e to the, we computed this integral to be 27 over 20. And so this is going to be 3,857 and roughly 43 cents. So the grand total from both these deposits is intuitively just a of 6. We're seeing what the 500 did after 6 years, and then we're seeing what the 1,000 does after 3 years. Add it all up. So it's 3024.82 plus 3,857 and 43 cents. And you get 6,882 and 25 cents. All right, so let me do this alternatively. And I'm doing it this way also because this is often how I see people do it on a quiz or exam, and I'm perfectly fine with you doing it this way. So let's instead kind of go, let's just say a of t equals the total in the account after t years. So let's just not break it up into 2 separate functions. We still cannot, I repeat, and I'm going to go back to this here. Sorry. We still cannot violate this rule here, so we're going to have to essentially use this formula twice. Once for basically from the initial time to after 3 years, t equals 0, t equals 3, and then we're basically going to have to like more or less reset the situation and think of the amount that we have in the account as our deposit in some sense, and then look 3 years after that. Okay, so as I said, conceptually it might be a little confusing, but if what I said makes sense, then it's definitely more efficient. I can't deny that doing it this way is more efficient. Okay, so right. So a of 3 after 3 years. So I'll just do it a little quicker. I'll just plug in, yeah, so here, my initial deposit is 500, all right? So I want to see what 500 grows to. So 0 to 3, the force of interest. Okay, but after 3 years, and immediately after this $500 grew to whatever, we deposit $1,000. So it makes sense to just add 1,000. Now we're looking immediately after the $1,000 deposit at the end of 3 years, so this 1,000 doesn't grow any. And so here we're using our basic formula right here just to see what $500 grew to. And we're basically employing common sense. We're using our formula, the formula right here. We're just applying that right here to see what the $500 grew to, and then using common sense to, and adding $1,000 to see how much is in the account immediately after the 1,000 deposit. Okay. So in using our rule just here, we're not, using our formula right here, we're not violating our rule that the formula doesn't make sense. It gives you garbage answers if you have more than one deposit in the time period. All right, so remember, delta of t is t over 10. I mean, we actually did this already, but you do this, you're going to get, well, we actually didn't do 0 to 3, but you can do this integral here, and you'll check that you'll get, well, 784 and 16 cents plus 1,000 equals 1,784 and 16 cents. Okay, so now we're going to basically reset the problem, and we're going to pretend that we have this basically new account where we make this deposit here. Actually, it's probably not a bad idea to circle it. We're going to pretend that we have this new account where we make this deposit of 1784 and 16 cents at t equals 3, and just apply our formula now. Okay, so applying our formula, kind of pretending we have this one single deposit of 1784 and 16 cents at t equals 3, so that our rule doesn't get violated. A of 6 is going to be A of 3 times, well, it's here, it's 3 to 6 delta of t dt. And again, that's just t over 10. And we got A of 3 here. It's just 1784 and 16 cents. Just barely squeeze that in. Let me move the E over. Okay, and so, yeah, and maybe I should, well, yeah, I should say this right here is going to be, it's actually e to the 9 over 20, t squared over 20. Plug in 3, you get 9. Plug in 0, you get 0. So it's, or t, 9 squared over 20 minus 0 squared over 20 is 9 over 20. So this here is going to be, well, you do this integral here, it's going to be 36 minus 9 over 20 So it's 27 over 20. And you get, you dump this into your calculator, 6882, and well, same answer. So let me double check this real quick. Make sure the rounding is 100% correct. Just from rounding, it might be off by a penny or two. Well, okay. So if you do it this way, you probably, let me do a better job rounding, actually. Yeah, so you're going to get answers that are a little different if you don't round, because you're using this number to do this computation here. So this is 15,609. So this is 15,609. Not that it matters for a quiz or exam, but I just want to emphasize that you do get the same answer. All right, so yeah, this is 15,609. It's a little hard to read. So 3 to 6. And so, yeah, this is going to be 1784, 15,609, e to the 27, 20. And let's check what that is. Yeah, now you get exactly the same answer that we had before, 16,882 and 25 cents when you round to the nearest cent. Okay, so yeah, two different ways of doing the same problem. Again, this way is quite a bit more efficient, I think, but conceptually it might be easier to break it down into these two kind of pieces and do each piece separately. Up to you.